Slowly with some introductions, right? I think the clock is a little bit wrong. I think it's 3:30. So, but I think it's a good time to start. So we have the pleasure to have today Vijay Gupta from Purdue University. It's also a personal pleasure for me because as I have said already to several people that we met together with Vijay, we know each other for 10 plus years, at least as a PhD student. I have cited a lot of his papers on sensor scheduling. So it is really nice to finally have you here. So Vijay did his undergraduate degree from IIT and Delhi, then he moved for a master's and PhD at Caltech, and he had a wonderful career with accumulating some of the best and most prestigious control awards, like the Ekman Award from CCS and the Antonio I believe, yeah. Plus, of course, NSF career and all these things, which nowadays I think it doesn't matter at this seniority level, and several best paper awards, like in, for example, in ACC. So he works on distributed systems with application in robotics and energy systems and learning. So it's a pleasure having you here, yeah. And yeah, I look forward to the talk, all of us.
Well, thank you very much, Vasilis, both for your kind invitation and then the introduction. It's always a pleasure to come to Michigan. Many good friends here over the years and mentors who have, like Jim, who have helped me all through my career. So it's really, really great to come here. What I'm going to present today is some of our recent work with my postdoc Shivam Bajaj and colleague Caroline Beck at UIUC. When I've timed it, it's supposed to be about 45 to 50 minutes. So I welcome questions in the middle. If it's some part that is better left at the end, I'll indicate that. But please feel free to stop me in the middle and so on. So model order reduction is a classical problem, right? We have classes of model order reduction. When I teach model order reduction, and I'm sure many of my colleagues do, the problem that we start with is given a model of high order, which for dynamical systems perhaps almost always is in terms of state dimension. Obtain a dynamical model of lesser order such that for the same input, the outputs are approximately similar. So I start with this system, X is of very high order, and I want to obtain an XR, X reduced, so that if I apply the same Y, then Y minus YR is small in whatever metric we want to have. This problem also shows up in other fields where perhaps the model is not dynamical, but essentially the issue is the same. The fundamental motivation is the same. There are lots of many good methods available, especially for linear systems. The importance of this problem really is that it is computationally much better to run this reduced order model and get a sense of what is going on in terms of the outputs for analysis. But what is often, said, but not really in these words, is that this reduced order model would also be good for synthesis. Right? In other words, when we get this reduced order model, we can forget all about our infinite dimensional model. We can take this small model and we can design a good controller, and we'll, hopefully, if the distance is small enough, it will work well on the original model. Right? And as I said, balance truncation, moment matching, gap metric, lots of many good methods are available. And whatever I say today, whatever I propose today, should not be taken in any way as something better than these methods, right? In fact, I will explicitly say that whatever I say today can be seen as a complement on top of these methods. So if you like any of these methods, I've got no beef with you. So the motivation, at least for me, for this problem started from my interactions with some colleagues who in semiconductor manufacturing. So they won this Smart USA Institute from SRC, Semiconductor Research Corporation. And at some point, the Department of Commerce was also involved in this. And they were interested in building digital twins for smarter semiconductor manufacturing. So digital twins have been used and proposed and used in a variety of things. Infrastructure systems. People have talked about digital twins of smart cities. Apparently, there is a company that says that we build such twins, and you can also find claims that use of these digital twins has saved some, helped in monitoring some real world infrastructure systems and so on. So a digital twin is essentially a model. It's a very high fidelity model, perhaps. And that's certainly the context in which the semiconductor manufacturing people were interested in. They wanted to build for all their physical processes that were going on in terms of building their semiconductor chip. They wanted a numerical model for that they were saying would help them in a bunch of things. So when we were brainstorming and we asked what sort of things would you be interested in, you can kind of think about 4 different parts of this, right? So you can say we can design and optimize, right? So finding a new material for making chips takes about 10 to 15 years right now. And according to semiconductor manufacturing colleagues, that is unsustainable. There has to be 3 years, 5 years, right? Because the demand is growing so quickly. So I would say that is an offline application, right? I mean, so you do lots of experiments, and perhaps instead of building everything in the real world and optimizing the parameters and so on, you can optimize the parameters over simulations and do it more quickly. You can think about predictive maintenance, right? I mean, and my belief is that this is the original context in which digital twins were proposed, that you have a jet flying, and instead of tracking the jet every time, you can track the sensor output, and you can feed that into your computer simulation to figure out whether the jet would need some predictive maintenance, and you can have a twin for each individual jet. And so this is kind of online because you're getting real data and you're integrating that into the simulation, but not real time, right? Sort of be a little bit off, it's completely fine. You can do post hoc analysis, and that again is what went wrong. And again, what if simulations are very useful for that, and that's all fine. The thing that my semiconductor colleagues were interested in was this one, the real-time control and troubleshooting. So they said that sometimes we are running through this very complicated process, and we know our sensor is telling us that something has gone wrong, right? So a 3D printing of an antenna might take 17 days, right? And on day 15, we know that the temperature is not what it was supposed to be. But we don't know what to do about it. It's such a complicated system that we just don't know how to take care of it. So what we want this digital twin to do is then figure out what has gone wrong, so troubleshoot, and then suggest to us what the corrective actions, if any, could be. So real-time control. Okay. So now we are talking about an online and real-time. Right? So we are talking about something that has to go perhaps slightly faster, ideally faster, but at least at the same speed as a real system, and keep tracking it and tell us what has gone wrong, right? And then what can be the corrective action for us to reach the desired state. Now, you can think about this in a variety of contexts, but this is the motivation, right? I will not solve this problem of semiconductor manufacturing. That will take a community many years, but this is the motivation from which I will start my reduced order model. So to summarize, what I'm saying is that there is a space for very high fidelity models, perhaps in offline analysis. There is, of course, the real system, which is the ultimate truth, but it's very difficult to do experiments there. And what we are talking about is this domain here, where the model is reduced order because it has to run in real time. And then it has to be used for real-time troubleshooting and control. Right? So there's a space for all of these, and my focus is going to be here. So what do we need from such a reduced order model? Right? So if you look at gain systems theory, there are 2 requirements that have been traditionally made. Right? One is that for the same input, U, the difference between Y and YR should be minimal, ideally with provable guarantees, but at least it should be a close approximation, right? And so, guarantees are given by balanced truncation, and that's why balanced truncation is very useful and very popular. Another requirement might be that it is computationally inexpensive, right? That we don't need to, spend so much time solving for this reduced order model that we can't do it for real systems. And again, moment matching, for example, is a perfect example for such a method. But for real-time troubleshooting, I would say that there are a couple more things that we would want. Right? And the point is that when some disturbances happen to the plant, right? So now my system is no longer x dot equals say x plus bu, but this other disturbance d has come in. What I would want is that my system somehow keeps tracking this y. right? If it keeps tracking this y, then I have some hope of being able to design a controller that will bring it back to my desired output. If I lose that y, well, whatever control I'm designing on the reduced order model has got nothing to say to the full order model, because I'm no longer tracking what is going on in the disturbance model. This is quite different, for example, from its use in, let's say, security. In security, what you would want is if there's a disturbance and an adversary hits the real system, its output diverges, and your model does not diverge. Your model, there is a huge difference. So I can say, well, something weird is going on in the real system. Here, I would want it to continue being a good reduced order model for the system which is perturbed, right? So I should be robust to disturbance and modeling errors. My reduced order system now, I need to do something to it, but how do I do it so that YR continues tracking Y in spite of this disturbance being present? That's requirement number 3 that I'll impose. Requirement number 4 I will impose is that in that case, any control that I design that brings my YR back to my desired trajectory should then work on the real system. I should use it for control design, right? And perhaps, given that these are, a semiconductor process can consist of like 50 sub-processes, perhaps I don't want to design one, giant reduced order model in one fell swoop. A vendor might decide to update one part, and so I should also only be updating that reduced order. There should be some compositionality that is there. A different way of saying compositionality is, suppose I have a system that I know is a series interconnection of 3 systems, then I want my reduced order model to have series interconnection of 3 systems. If I just do a balanced truncation of 3, that might not be present. So unfortunately, classical methods may not satisfy these requirements, right? So we can quite easily see that, right? We take very simple or full order model, cart with double pendulum. I introduce this disturbance. It's quite clear that this system, the same system, is not going to follow the system with disturbance, right? The dotted model is with disturbance, and of course, it's not going to follow the original system with disturbance because I'm not taking the disturbance into account. Now, interestingly, even if I take the disturbance into account, I say that I know the disturbance, but I take the same reduced order model and I plug that in, it may not work. So this is a balanced truncation method. Again, it's a fourth order model. The details of the plants are not important. But what I want to show is that I designed a second order reduced order model. It was pretty good. And then when I plugged in the disturbance, and I did the reduced balanced truncation of the same plant to order 2. And with disturbance, the error was huge. Okay, so the modes that were important without disturbance may become important with disturbance. And hence, the reduced order model may not remain a good reduced order model.
Next question is the idea I have in my mind is when you do balanced truncation, you're projecting the state. And so if E is in the null space where you're doing the projection, you're never going to see that effect of that disturbance. And is that
that's kind of the intuition, right? I mean, traditional models cannot preserve structure, right? If I take a transportation network and I do the reduced order model, I will not preserve the arteries, and I'll not preserve the highways and so on. There will be no graph preserved, right? And really, sort of the reason really is that even if you do balanced truncation, you're doing all sorts of inverses and multiplying with things, and this destroys any structure that is there. So either way, you will not. Even if your original system has a nice linear structure, you will not get any interpretability in the reduced order model. And if you do the reduced order model of each structure and combine them, you will not get a good reduced order model of the original system. So another way of saying the same thing is, suppose I start with the cascade interconnection, right? I'm asking if I do a reduced order model of G1 and G2 and interconnect them, versus I do a reduced order model of G1, G2, the overall system, are these two equivalent? And it's quite easy to see they are not, right? I mean, I can start bounding sort of the difference terms in the two system, and I quickly find that it's not possible to write it very neatly. It's not possible to relate these two. In fact, you get terms which have coupling, right? So the modes that were not important for G1 alone, they become important because G2 feeds into them. And this is cascade. There's not even feedback, right? This is like a very simple interconnection. And it's not even the correct causal direction, right? I can't even start from G1 and keep doing it one by one. I sort of effect of the following plants are showing up on the plant. So, you can do it for feedback, and feedback, one particular case of feedback is controller design. And so controller designed using reduced order model may not even stabilize the full order. You have to do something special. Gap metric is one way of doing that. What I'm going to present is a different way of doing that. But in general, balanced truncation moment matching may not satisfy this. All right, so the core idea of our approach follows now. So in a traditional approach, what we do is I have a system sigma 1. I have designed its reduced order sigma 1R. The question I'm asking is, if there is an initial disturbance, what should I do here? How should I continue tracking the system? Why does the traditional approach not work? Because if disturbance is small, perhaps we can rely on some continuity, some input to state kind of stability kind of thing. But if disturbance starts depending on X, unmodeled dynamics, effects of other subsystems, things like that, then errors can accumulate over time. So we need to somehow track what is the effect of disturbance. But the disturbance is not available to us. Since we don't have access to unmodeled disturbance, so since I cannot feed the same disturbance here, I can try to estimate it, but estimation is also through Y, and sort of if, for example, we are in a feedback structure where there is an error in estimation of D1, that feeds into error in estimation of D2, and it kind of keeps going back and forth, that can blow up as well. So instead of what we suggest is that we think of designing an artificial disturbance here, which disturbance will make sure that this output of the reduced order model is similar to the full order model. Okay, think of this disturbance as a control input. So I'm going to perturb my reduced order model in a way that these two outputs continue to be the same as the disturbance impacts the real system. This disturbance at this point is completely arbitrary. It can be modeling error, it can be other systems, it can be whatever. Now, naturally, this D prime has to depend on Y. Right? So this is only useful, or this is more useful, perhaps is a better way of saying it, if my real system is running, I am getting what is the output of my real system in the presence of that disturbance. And I can use that to calculate this T prime. Okay? But the digital twin example is exactly that. My real semiconductor plant is running. It is giving me an output. It is telling me what the disturbance is doing to the real system. I can use that output and I can perturb my system. So it may not work for all applications, and I don't claim that, but at least for the digital twin example, I will suggest that this is a useful trick. Okay. So the way we'll design the disturbance is through this concept of simulations and biosimulations, and there are experts in this room and in Michigan more generally on simulations and biosimulations. We'll use this recent extension that considered non-deterministic continuous systems. Okay, so essentially it's a dissipativity type thing that they had. So if I have a system sigma 1, it has two inputs U1 and D1, and another system sigma 2, then they talk about two systems being similar, and they have this bounds gamma and delta, two parameters. The two systems are similar if I can design a disturbance D2 such that the difference between Y1 and Y2 is bounded in this way, right? So the difference is bounded. So as I said, it's a dissipativity type inequality, right? So it is bounded by how dissimilar the inputs are, Y1 and U2. That will come in useful because if we are in feedback, the output of one system is going to be the input of the second system, right? So the outputs are different. The effect of each input, and then the effect of each disturbance. Yeah. So we'll essentially use this notion to now do reduced order models. Yeah. So it guarantees that for close inputs, outputs stay close. Notice that this condition does not require the states of the system anywhere. And in particular, the states can be a different order. Right? It only requires the U and Y to be the same order as dissipative data. Right? And the difference in inputs, as I said, can be because the previous subsystem is replaced by reduced order model. So if you go back to where I started, right, in the reduced order model motivation, the motivation typically is for the same input, the outputs are close. If I have a disturbance, the inputs are not the same, right? And this takes care of inputs not being the same. That's sort of one reason why this might be useful. So as I said, if there is no condition on the states being the same order, I can have one as the original system and the other as a reduced order model, and I can say that given sort of stable systems, I need the stable systems because of dissipativity type requirement that I have. I can construct a gamma delta reduced order model if I can construct this driving input D2, the control input D2, such that the same condition is being satisfied. Can we find such reduced order models? I can define them, but can we find them? And again, given that these are linear systems and this is a dissipative inequality, perhaps not surprising that I can write it as a linear matrix inequality. So in general, I can write it as a problem that, you know.
We have an issue that let's try and put connection.
Sure.
This shouldn't be a reason from there, so I'm not sure. We can disconnect and connect it. But with a weird zoom in. Screen again. Works now. Okay, in worst case, I may set the zoom screen, but for now, sorry.
Thank you. So I can set up this optimization problem. I have to find my reduced order model, A to B to C to, and there are these dissipativity inequality matrices X and pi, and this gamma delta, which is the gamma delta ROM. And I want to minimize how different the outputs are, subject to the system being stable, the system that I'm trying to find being stable, and this sort of an inequality holding. Now, the first thing is that this is superfluous. We can show that anything that satisfies this inequality will automatically be stable. So that's a good thing. Unfortunately, this is still a BMI because I'm finding both X and A, right? So the system matrix is A to B to C2. So we can either live with BMI, or what I can do is I can start with given A to B to C2, which I can find with my favorite method, Allen's truncation or moment matching or whatever. If I care about computational efficiency, I can go for moment matching. If I care about, you know, kind of guarantees, I can go for Allen's truncation. Whatever your favorite method is, I can do that. And then I can just search for X and pi, which then becomes an LMI, right? So in other words, I can preserve whatever favorite properties, whatever the nice properties of your favorite system is, favorite reduced order model algorithm is, and add this on top. Right? So, you know, suppose we have the original system, and you know, I'm just summarizing whatever I said before, that if this LMI is feasible, then I will obtain a reduced order model. And this reduced order model will be robust in the sense that for any disturbance D1, I can ensure that the outputs are not too different. Okay? So I get this robustness on top. So now I go back to my original system, and now notice that I'm not changing this ARBR. what I'm doing is just adding this disturbance D2, which is not D. So I'm not assuming that I know the disturbance that has hit. And instead of this huge spike the disturbance was causing, I can preserve the reduced order model following the full order model with disturbance and without disturbance. Right? So without disturbance, also I inherit whatever the good properties of balanced truncation were without the disturbance. And similarly, the other algorithm, these are toy examples, but at least a sanity check is there. Notice that I'm choosing the same order. I fix the order too, right? I'm precisely using the same AR and BR. I'm not, because of this disturbance, I'm not doing balanced truncation all over again. I'm not doing that. Yeah. All right, so this can be used to track what the disturbance is, right? My plant continues to track the disturbed plant's output. The second thing that comes is compositionality. Because this disturbance can be due to the error from the previous subsystem, you can start composing these ROMs. Right? Every time you make sure that the outputs are close enough, and as you keep composing them, you keep continuing. Your bound becomes weaker as you compose a lot of systems. However, your bound still holds. That there is a bound that you still get. You don't diverge completely. Right? And so you preserve that interconnection structure. If you have the particular interconnections cascade parallel feedback, you can get stronger conditions. Those are in the paper. Each individual problem is the problem of individual subsystems, because I'm essentially taking each subsystem and reducing it. So I preserve the structure by design, by definition, and I get this bound overall. And as I said, since one interconnection can be feedback, you can think about this in the controller sense, in the control design sense now. Right? So I have an original system. I design the reduced order model. Now I design the controller. So this D1 prime is by design a reduced order model. So I design a controller, and I can, if I'm stabilizing this system is automatically going to be stabilized, because this system is going to be similar to this system. Okay. So the controller is designed for ROM, which is for the plant, not the controller in the plant. And now I can use the controller on full order plant, and I can ensure closed loop stability. I can also go for performance in sort of any output metric sense, because my outputs are close enough, right? I mean, I can talk about LQR costs and things of that sort. This is again a toy example, going from sort of 20th order system to second order system, and sort of the controller design with balanced truncation does not perform quite well. That's the blue one. The full order model is the red one, while our reduced order model, the controller that it gives, does perform quite well as compared. As I said, you can go for the performance. So you can think about, instead of perturbing reduced order model to follow the full order model, as we were doing earlier, now we perturb the full order model to follow this plant. Right? So I get the original system, I design the reduced order model, I do whatever controller design on this. Now I see this as the system that I have to follow. And so I can perturb my full order model here. This controller can be your favorite LQR or whatever controller you have. So any performance objective that is being met here can now be met here as well. Okay. So can call this sort of a, this ROM now is just simulated, right? It's the controller design depends on that. Controller is of the complexity of the simulated ROM, and then I have this perturbation to follow. And you can, again, come up with conditions that sort of you can track quite well. You can track to a set in YRT. You can also come up with, how far you are in terms of cost functions of LQR cost, because you know how far the inputs are, how far the outputs are. You can just go through that. And one thing that I would say is that, when I looked at the condition on the gamma delta similarity, the output bound depended on the disturbance D2 as well. So in some sense, it's a posteriori bound. I have to first determine D2, then I can calculate R. But you can get rid of that. That's not a big deal. That's what kind of this theorem says, that you can come up with a priori bound as well without having to design the reduced order model, see what disturbance is needed, and so on. So you can do all that. Okay. And again, if you sort of come up with very simple examples, if you have the full order model, which is perturbed with this disturbance, without proposed approach, it will actually diverge because of that. But in the presence of L2 disturbances, now we can talk about safety and extend to MPC formulations and things like that.
That's a good question. So the condition that you get, you convert this into like an LMI condition. It's, I guess, a bounded real lemma type argument. Mm-hmm. One of the objectives that you said at the beginning is you want this to be computationally efficient. So I'm just wondering about when you do these LMI approaches, the scaling with the state dimension, like at what point does this limit the size of the model that you can do this for?
Yeah, so I would say, that's a very good question. I would say two statements, right? One is that the reduced order model that is fixed. Yeah. And there is computational efficiency already in there because you're presumably using whatever method that you already find computational efficient. Now the LMI is an LMI, right? I mean, it is of the order of the stacked state, right? And so at some point, your LMI solver does not need it. We have been able to do it for, we are not LMI experts by any means, but, sort of a couple of hundred state systems have not posed problems for us, but I don't know how it scales to thousands or millions. I actually don't. So I will not go much into detail in nonlinear systems, but there is no reason for us not to do nonlinear systems. The basic idea is very similar. So, I have a system, I have disturbance hits. What perturbation I was calling the D2, should I have so that this continues following? And essentially, we go through differential dynamics. So differential dynamics is defined through taking these, essentially derivatives. Notice that these are not matrices. They depend on the state and, they can themselves be nonlinear. So we go through differential dynamics, and the core is that if the differential dynamics is gamma delta similar, then the original dynamics is gamma delta similar. And so we can work with differential dynamics now. And the advantage of differential dynamics is that now we can go to this kind of again, we get very similar system of equations. Now it's really an infinite dimensional system, right? Because we are working on the entire space of nonlinear. So either you go to SOS and try to solve it, or you just grid state space up and try to solve it, or if you have some other structure that you can utilize, right? So, while we can reduce the BMI to LMI, and we can think about sort of, what are the conditions for feasibility and things of that sort, I would say that computationally here, there is a problem, as in pretty much any nonlinear model order control reduction algorithm. There's fundamental issue that is there, right? I will just make a small comment here that so far in my talk, and in the following part of my talk, I'll be talking about reduced order model. But really at this point, you can think about the second system as being obtained as a linearization of the nonlinear system, as a, ignoring the delays that are there in the original system, as ignoring the actuator saturation that is there in any approximation, and the framework would still hold, right? So I would just make that comment. It's a more abstract model than. So yeah, if you take heat equation model and things like that, it performs quite well. We have done Mood-Kritzer model, and this is for a linearized model and performs quite well. But there is this underlying problem of computational complexity that, unfortunately, it has not been fully resolved. I think we can do interesting systems, and I think we can, be able to do like 100-order RC circuit kind of models. But yes, I mean, ultimately there is a problem that.
Can I ask for some intuition? If you go 2 slides back, where essentially you said you have the linearized, models, and then do the gamma delta. I achieve gamma delta similarity. Can you bound a priori the gamma tilde and the delta tilde?
Yeah. So, first of all, these are not linearized, right? So because this AI is right.
I mean,
right. So,
I mean the differential dynamics. Excuse me. Yeah.
So can I find a priori the gamma delta.
How essentially, if you tell me that the gamma is 2 and the delta is 5, let's say, what will be an intuition of how bigger potentially will be the gamma tilde and the delta tilde?
Yeah. Very nice question. At this point, we just solve the optimization problem. We don't have an intuition, but that's a very good point.
Yeah, thank you.
All right, so I'll conclude at this point. I posed a particular problem in reduced order model design, which is motivated by having a simulation or an environment in which I'm using the reduced order model to track my full order system. My full order system is running, and hence its state is, or its output is available to me at all times. And what I want my reduced order model to do is to track the state of my original system. And then I want it to be useful in the sense that if I design any control on that reduced order model, that control should also work on the full order model. Right? So that was the problem I imposed. And I said that using these notions of similarity and bisimilarity provides us an analytical framework for solving this problem. It can be utilized with our favorite reduced order model method. And so whatever the guarantees that we had on error bounds or on computational inexpensiveness will inherit that. But in addition, we'll get this robustness and the compositionality properties that can allow us to use for control design of our original system. This is all I had. I thank you for your attention, and I'll be happy to take any questions.
Yeah, please go ahead. Yeah.
Thank you. Wonderful presentation. To find how similar the reduced order model to original one, you solve this optimization problem to find parameters gamma and delta. Is the solution to this problem unique, or is it multiple solutions? And
yeah, so
this is the first question. And a follow-up question: what is the physical meaning of gamma and delta? Just I'm sure you brought it up before. Maybe I just missed it. But
yeah, no, excellent question. So it is not unique in the sense that gamma and delta. So if I think about this as a dissipativity kind of inequality, then these are like really gamma and delta dissipativity indices, right? So I am saying that gamma and delta gives some freedom in terms of how much. And now you can imagine that since there are multiple parameters, there is actually a set of gamma delta which will work, right? And that is why in the optimization problem, we actually try to minimize them, right? So no, the answer is not unique because it's a set that will work, and you need to choose any point. And depending on kind of what point is, what in some sense you want to reduce the conservatism, reduce the flexibility, reduce the tube, and so you try to minimize that. Does that answer your question?
Yeah, but what does it mean that gamma is minimized at the expense of delta and vice versa? Because it's not unique. What does it mean?
Yeah, really, this is a if you think about this, so this is the control energy that is going in, and this is the difference. In our examples, we have found that minimizing this gamma is slightly more important in terms of ensuring that in sort of y1 and y2 go down. But at the end of the day, these are different parameters, and sort of you can. There is really no sort of unique way of doing it.
I have a question. Can you remind me or remind us, what do you assume for the noise? Is the noise known, the D1 is known, and then you are finding a D2, or the D1 is just a finite energy signal?
The latter, the finite energy, L2.
Then you don't have an identification problem there for the D1?
So, I mean, what should happen is that the effect of DI should show up in YI.
Okay.
Right?
So it's like an internal identification problem. Yeah, right. It goes through because you care also about Y.
Yeah.
The Y is too much. So
right.
You don't care about the X, you don't care about the internal or the external signal. Okay, I think I get the intuition. Yeah. Thank you. Yeah, that's actually pretty
Here's a
cool.
question. You don't know the D1, but you at least know the model for how it's entering into the original model, right? You have the E matrix, which is the input matrix associated with D1. What if you said, I'm going to do balanced truncation, but not on the mapping from U1 to Y1. I'm going to do it on the mapping from the coupled U1, D1 to Y1. Then I'll get a reduced order model. Yeah, and I'll get error bounds on that. Like, why is that not sufficient? What breaks down?
It would be sufficient if you do balanced truncation on this system now, right? So you just say, this is my system, and this is what I'm going to do balanced truncation on, but you would need to know that exactly the disturbance.
I see. You'll get a reduced order model, you get an AR, BR, ER, but you won't know what the disturbance is, you won't know what to do with that.
Right. And if you say something like, previously my order 2 was working, I'll restrict to order 2, it may not. Or if I just use AR as the same and I'll just do BR, ER or something like that.
Yes.
I know you said this is not your application, maybe this is not a fair question. How well would this pipeline propagate if the full order model I start with is a little bit uncertain?
Beautiful question. I don't know. I think that ultimately this inequality that we are talking about is in terms of inputs and outputs. So the LMI may not work. The basic intuition of using that similarity still works. Now, going from, my guess would be that you can you can augment the LMI to take care of that robustness. I have not done it, but it's a very, very interesting.
If I may ask a little bit to add on this question, because it was relevant at least to what made me ask the first question. Then if you have this model error, right, or this uncertainty, right? This uncertainty is a model error. Why is not just, part of your D1, right, of your disturbance? So if it's essentially an error that it's L2, right? Then it's not handled automatically, then the answer is not that already your approach handles.
So as long as it will be, it can be modeled as like an additive disturbance, additive uncertainty, it will be handled.
Yeah.
But if it's a nonlinear system showing its L2 and so on would be problematic in itself.
What about the assumption extending it to non-linear system?
So we still need, the assumption that we need is still incremental stability. That's similar to the zero asymptotic stability, we need incremental stability.
Talk at all about the case where the system's unstable? I mean, there are variants of like balanced truncation for unstable systems.
Yeah, the dissipativity framework will start breaking down. So we can't use that. We have to assume, and this was something actually we made an error in our first draft of the paper and the reviewer pointed it out. So then we went back and checked, yes, we had made an error.
Other questions? The final question was relevant to the stability on my side. I was going to ask that the intuition of the stability is essentially this allows you to handle the L2 errors, the L2 disturbances. So this is why you want this kind of stuff. It relates to that also this notion of y1 minus y2 metric that you have this gamma delta essentially definition.
Right.
Yeah. Okay. Yeah. Thank you. So if there are no other public questions, let's thank the speaker. Talk, it was the most clear, concise talk.
I was worried the audience is not getting its money's worth because I finished in 40 minutes. Next time, add more slides here.
No, that's lovely. Thank you so much.
Well, have a good drive back.
Thank you. Thank you so much.
I
Nice to
think
see you.
yeah, it's like, oh, is that a pretty question?
I need to. Believe in working days has changed. I'll still.
Then, bye bye, yeah, we can.
No, really.